Yeah, so thanks, George, and thank you to the organizing committee for giving me the opportunity to present my work today. My talk today will be perhaps slightly different from what we've seen so far, although it will treat a problem that many of you will be familiar with and that's been mentioned before, which is nonlinear amplification. It could be of energy, but it could be also of other quantities, as we will see. This is joint work with David Goluskin from the University of Victoria in Canada, and it's actually been published in Science Journal of Applied Dynamical Systems. So if you're interested, you can find a lot more in the paper. So the motivation behind this work, as I mentioned, is to quantify nonlinear growth. So as George Rigas mentioned in his talk, we're interested in growth of perturbations from, say, a laminar flow for stability reasons or transitions. And in this case, we want to know how much a certain perturbation can grow, and we're interested in minimal seeds and things like that. But there are also other examples. So here I'm giving one from optimal mixing, which we've seen mentioned in the last talk. So in this case, we have a laminar channel flow with a nice parabolic profile, and in the fluid layer, we have two different chemicals, which are neatly arranged in two layers. And the problem is as follows. We're given a budget of energy, and we want to perturb this flow in such a way that as it evolves in time, then the two layers of chemicals are mixed as much as possible. So there are two main questions here. The first one is, given the energy, how should we kick the flow to get the maximum mixing? But also, what is the maximum amount of mixing that we can get for the given budget of energy? Right. So there are more problems like this. What I would like to do is consider them all by putting them all into a general mathematical formulation. So in this case, I'm going to consider some dynamics governed by a differential equation, dx by dt equals f of x. X here could be the state of the system, so it's a long vector that contains the flow velocities at various points in the domain, the pressures, but more generally, it could be any reduced order model of a flow or any dynamical system. So this formulation is quite general. The problem that I want to consider is to find the maximum of a quantity phi, which could be energy, but it could be mixing, it could be other things. And we want to maximize this quantity along all the solutions of the differential equations over time, where time goes from an initial time 0 to a time horizon t, which could be finite, but it could also be infinite. And then we also want to maximize over the initial condition little x naught, where this initial condition lies in a given set, which is denoted by this curly x naught here. Right, so if you've looked at this problem and you've seen the application, you might think that you know how to solve this, right? This is kind of a classical problem, and it can be attacked by adjoint methods and adjoint optimizations. So you can compute an optimal initial condition, x naught star, and an optimal stopping time within the time window, t star, and that's great, right? The main problem with these techniques is that when the differential equation is nonlinear, or the quantity phi is nonlinear, then this maximization problem that we want to solve has lots of local maxima. And adjoint optimization is a gradient method, and so generally it converges to local optimizers. So in general, what one computes with adjoint methods, it's just a lower bound on the global optimum, which I'm going to denote phi star here. Right? But we have no way to know whether we've actually attain an equality here, or whether we've just found a strictly lower value for our observable. So what I would like to do is go at the problem from the other side and compute complementary upper bounds on this maximum phi star. And the way I'm going to do this is by using convex optimization, even though the problem I really want to solve is nonlinear and non-convex. And in particular, I'm going to use convex optimization to optimize auxiliary functions. So these are functions which I denote v, which depend on time and depend on the state variable x. And the idea really goes back to the work of Lyapunov on stability. So if you're familiar with Lyapunov stability and Lyapunov functions, you will see some parallels with that. And really, what allows me to do this is the fact that we can check how such a function v of t and x behaves along trajectories of the system by writing down some conditions, some inequalities, but without actually having to solve the differential equation. So I can try to optimize, consider these auxiliary functions v without having to run simulations, without time stepping, but instead using tools from convex optimization. So the point of the talk would be to illustrate how to do this. There's going to be a technical assumption that I'm going to make straight from the beginning, which is all trajectories, all solutions of the differential equation that start from my initial set, curly x naught, remain into a region of phase space, which I'm going to denote omega. This could be a big ball, for instance, if all my trajectories remain bounded. But if I didn't know what this omega is, my worst guess would just be to take the full phase space. I could always do that. Right. So the main result at the heart of this talk is the following. So remember, I want to find an upper bound, let's call it u, on this maximum amplification of the quantity phi, which I denote phi star. And I can prove, I'm not going to do it, but I'm going to just state the result. So I can prove that this bound holds if I can find an auxiliary function v, which satisfies the three conditions that I've shown here. So the first condition just states that my observable, the quantity of interest phi, is bounded by v at all times and at all points in the region of phase space where I'm interested in. The second condition looks a little bit more complicated, but really what it states is that the time derivative of v along the trajectories of my dynamical system, of my equations, is negative. And this means that v decays in time, essentially. If I were to plot the evolution of v along a solution, the value of v could not increase. The third condition simply states that my function v at the initial time and for all initial points is bounded by the constant u. So if I can find such a v, then the constant u is a bound on phi star. Now it looks like I've complicated the system. I started off with a nice this problem description, which we're all familiar with and which we can understand. And I've introduced these auxiliary functions that make it look more complicated. But there's a very good reason for doing that. So the first one, which I've already mentioned, is that these conditions on the function v and the constant u are imposed pointwise in time and in state space. So this means that I can try to check them without having to solve the differential equations, so without having to run any expensive simulations. The second important condition is that looking for a v and a u that satisfy conditions 1 to 3 here is actually a convex problem, right? You will see that really the name of the game is to find the function v that gives the smallest possible u. And this is an optimization problem which is convex. And this is true because the conditions depend linearly on the variables v, which is actually a function, and u. So by switching from trajectories to auxiliary functions, I've switched from a non-convex nonlinear problem to a convex one. And it turns out that in many cases, if all these functions that appear in these conditions are polynomial, then this problem is actually computationally tractable. So we can optimize these auxiliary functions numerically. So just a few words on how to do this. We have our optimization problem for the auxiliary function and for the bound. And let me assume that the observable phi and the differential equation, the right-hand side of the differential equation, are polynomial functions. Now, you might think that this is a restriction, but if you look at reduced order models of the Navier-Stokes equation, so discretizations of the Navier-Stokes equation, this is true, in most cases at least. The second assumption that I want to make is that this auxiliary function v is also a polynomial, and I'm going to choose it to have degree d, where d is an integer that I can choose, or less. And then finally, my sets, the initial set curly x naught, and the region of state space omega must be defined by polynomial equations or polynomial inequalities. Again, this might sound a bit abstract, but you should think of, for instance, the set of initial conditions as having a fixed energy or a fixed distance from the origin, let's say unit energy here. And the region of state space of interest, say a ball of radius r. Now, if these three conditions are satisfied, then the optimization problem at the top of the slide is a polynomial optimization problem. And it turns out that it is difficult, but I can construct a solution, not the exact optimal solution, but a feasible solution. So I can construct a V and a U that satisfy the constraints using techniques from what is called sum of squares optimization. Now, I won't go into the details of this. They're technical and there won't be time. But these techniques are very well known, say in control theory or in operations research and in numerical optimization. And if I apply these techniques, what I can do is compute an upper bound, which I'm going to denote U star D, where D is the degree of my auxiliary function V. Now, I can repeat this operation for different values of the degree D, so I can keep increasing this. And in fact, what I find is a sequence of upper bounds, which can only get better as I increase the value of the degree of the auxiliary function. And remarkably, what you can prove is that under some technical conditions, so for instance, the time horizon t being finite and the initial set and the region of space being compact, for instance, if this is true, then you can prove that these upper bounds converge to the actual global maximum of the original problem. So here I want to pause for a second and just consider again what I've just said. So I have the value phi star, which is a solution of a nonlinear, non-convex optimization problem over trajectories. And what I can do using auxiliary functions is approximate this value with arbitrary accuracy just by solving a set of convex problems. Now, if you're thinking that this sounds too good to be true, you'd be correct because there is a catch. And the catch is that the computational cost of this SOS, sum of squares methods, grows quite quickly as the degree D increases, but also in terms of the size of the state space, so the number of variables in the state X. So if you want to implement this in practice, you can only do it for low-dimensional ODEs, so very low-dimensional, simple reduced order models of fluid flows. You would certainly not be able to do it for discretizations of the Navier-Stokes equation with millions of degrees of freedom. So this is the catch. Nevertheless, the method is interesting, and the results, as we will see, are pretty good. So just to fix the ideas in a nutshell, the method started off by considering, we considered a nonlinear optimization problem for phi star. We reformulate it into a convex problem using polynomial auxiliary functions to obtain the problem at the bottom. And then we attack the problem with sum of squares optimization to compute a convergent sequence of upper bounds on phi star, where the convergence is subject to terms and conditions from a mathematical point of view, but in practice, it occurs even when these terms and conditions are not satisfied, as we will see. So in the remaining 2-3 minutes that I have, I just want to show you some results for a simple model of shear flow, which was proposed in 2004. It's a model of a flow between two parallel plates, which is driven by a sinusoidal forcing. And the model is obtained by projecting the full velocity field into just 9 spatially varying modes with time-varying amplitudes A1 to A9. One can derive equations and ODEs for these amplitudes from the Navier-Stokes equations, and they have a Reynolds number, they have a body force B, there are some linear terms, and there are some nonlinear terms which are quadratic, just like in the full Navier-Stokes equation. This reduced model has an equilibrium, which I call A sub L. I just want to point out here that the state in this example is called A for amplitude, but A is what previously was X. So I was saying we have a linearly stable laminar flow, which corresponds to a sinusoidal flow profile, as shown in the figure. And the problem I'm going to consider is the amplification of the distance from this laminar flow, so let's say a perturbation energy, amongst all perturbations that have unit initial energy. So this would be my initial set. Anyway, so the model that I want to show examples, the example for is a 9-dimensional model of shear flow between parallel plates, which is driven by sinusoidal forcing. It is obtained by projecting the full velocity field onto 9 moids, u hat I, with time-varying amplitudes, A1 to A9, which satisfy an ordinary differential equation or a set of ODEs, which can be derived directly from plugging these approximations into the Navier-Stokes equations. The model has a linearly stable equilibrium, which represents a sinusoidal laminar profile, laminar flow as shown in the sketch, which corresponds to a particular choice of modal amplitudes. And what I want to look at is the amplification of the energy or the distance of perturbations from this laminar flow. So my phi is just the distance from AL, and the initial perturbations will have unit energy. Here I'm using A to denote the state vector for amplitude, but here A is what previously was X. So this problem can be solved with adjoint optimization to find local maximizers. And here I'm plotting the best local maximizer that I could find. What these results are telling us is that the true value of phi star lies somewhere within this region that I'm shading. But we don't know whether the black line is actually the global maximizer or whether there is a better one. So to try and conclude that, I'm going to compare the results of adjoint optimization to my bounds. And I've computed them using an infinite time horizon and a time-independent auxiliary function v, which only depends on the state. So for polynomials of degree 4, this is what we get. You can see that now we can conclude that the true maximum only lies in this region here that I'm shading. Interestingly, because I'm working with infinite time horizon, you can see that these upper bounds blow up to plus infinity at Reynolds just above 40. This is an artifact of the fact that I'm working on an infinite time horizon for these computations. But I can increase the degree of V and obtain much better results. And you can see now that the upper bounds from auxiliary functions and the lower bounds on phi star from adjoint optimization agree very well, which confirms the global optimality of the adjoint method. But this could not be known in advance. Again, you can see that at certain Reynolds number, the bounds blow up. But if I go up to degree 8, then the two curves essentially coincide throughout the entire range. I get similar results if I repeat the computation over a larger set of Reynolds numbers. In this case, for technical reasons, I can only go to finite time horizons, which I fixed to 10. This is because the laminar flow for larger Reynolds stops being globally stable, and so the system becomes turbulent. But again, you can see that throughout the entire range, the bounds upper and lower are very, very similar. They agree very well, and this confirms that the adjoint methods converge to the global optimum, which we couldn't know otherwise. So this is all I want to say. I think I'm running out of time. I'll leave my take-home messages on the slide. But I just want to mention that there's more to be done. Obviously, one open question is how do we handle high-dimensional ODEs, which is the main drawback of this approach. But there's also more in terms of how can we extract global optimizers from optimal auxiliary functions, and how can we apply these methods to PDEs. The theory goes through, but computational methods for PDEs are lacking. So if you're interested in hearing more, just drop me an email, or you can have a look at the paper, but I probably should stop now. And if you have any questions, I'll be very happy to answer them.